Welcome back to trigonometry. Today we are going to do some equation solving, much using techniques that you basically learned in your algebra classes, but now you're applying them to equations where you have trig functions in them. So we're going to be solving trig equations. Now these trig equations are going to look a lot like the identities that you've been verifying, but big key difference is, an identity is an equation, it has an equal sign, but you're assuming that both sides already are equal for any values, for all values possible, for x or theta or whatever. And when you verify, you're basically going through a proof process and showing, yes, this is true. But what we're going to be doing here is dealing with conditional equations, where we have to figure out what conditions make the equals true. So what conditions, in other words, you're solving and figuring out what values for x or values for theta make the equals true. So if these equations, when it's asking you to solve, not any value can go in there. You're trying to find the values. So we're going to go through and look at several specific techniques to use for finding such values. And with trig equations, you have to be especially careful and look at what domain they want you to be within. So if they say all possible values, that's different than saying, okay, all values within the interval from 0 degrees to 360 degrees. You know, there's some differences there. So you can end up with multiple answers depending on what interval your solution needs to be found in. And if you think about it, like when you're doing sine, cosine, tangent, if you think about the unit circle, you know, if your sine equals some positive number, like positive 1/2, then you've got, within 0 to 360 degrees, you've got two possible answers. The one found in quadrant 1 and the one found in quadrant 2. So you've got to look at your interval very closely and think about your unit circle. And think about what's happening with the angles. Okay, well that's enough of me yapping. Let's go ahead and start just looking at some examples. We're going to go through and I'm going to do an example for each type, each category. And you're going to start to recognize these categories from your algebra classes. Okay, so the first problem we've got, we're going to use linear methods. Basically same kinds of methods you learn in basic algebra, intermediate algebra, when you solve linear equations in one variable. But we're going to use similar methods here. Our tangent theta, theta is our unknown, our variable. We got a tangent theta here, no crazy exponents or anything. So we're going to solve this equation like we would any other. We're going to add square root of 3 to both sides. We're going to divide by 3 on both sides. And then to find theta, we have to do the inverse tan of square root of 3 over 3. Well, if you want the answers over the interval 0 degrees to 360 degrees, you've got at 30 degrees, your tan is positive square root of 3 over 3, and also at 210 degrees, your tan is positive square root of 3 over 3. Now if they ask you for all possible solutions, you've got 30 degrees. Well, if you add 30 plus 180, you get 210. If you add another 180, you get 390, which brings you back to where 30 is. And then, you know, each time you add 180, you're either going to be at the 30 degree place or at the 210 degree place on your unit circle. So we'll say this: 30 degrees plus some multiple of 180, where n is an integer. So that's all possible solutions right there. Okay, so that's an example of using linear methods. Here's one that has two solutions over this interval, or there's actually infinite solutions if you look at all solutions, but they all are going to be some 30 degrees plus some multiple of 180. So like if n is 0, that's just 30 degrees. If n is 1, it's 210. If n is 2, then it's 390. If n is 3, then it's then from there 570, you know, and so on. But they're all going to fall on the unit circle in these places. Okay, now they're all not going to just be that straightforward. Sometimes you might want to use factoring to solve. Like let's say you have cosine theta cotangent theta equals negative cosine theta. Well, if you add cosine theta to both sides, you can get this into a form that's factorable. Because you can factor out cosine theta here. And then just like any equation in algebra class where you solve by factoring, as long as you got 0 on one side, you can set each factor equal to 0 and go from there. So cosine theta is 0, or cotangent theta is negative 1. Okay, so let's say we need to solve these over the interval from 0 to 360, 0 degrees to 360. Well, cosine theta equals 0 on that interval at 90 degrees and at 270 degrees. Cotangent theta equals negative 1 over that interval at, let's see here, 135 degrees and at 315 degrees. And that's all the values that work over that particular interval. Okay, now your factoring is not always going to be linear factors. You might have quadratic factoring. Let's say you have something like 3 sine squared x minus sine x minus 2 equals 0. Well, this is quadratic. You got sine squared x, sine x, some constant. So being quadratic, let's see, this one is factorable. Treat the sine x as if it's your variable. One times 2, put a 1 here, no, put 2 here, put 1 there. Minus and minus, so let's make this minus and that plus. These two factors equal 0, so you got 3 sine x plus 2 equals 0, which means sine x is going to equal negative 2/3. Then you got sine x minus 1 equals 0, so sine x equals 1. Okay, now let's say we're told to do this over 0 to 2 pi. Well, sine x equals 1 at pi over 2. But sine x equals negative 2/3, we're going to need to use the calculator for. Alright, let me check my mode. Since we're doing it over 0 to 2 pi, we're doing things in terms of radians. So I better make sure I'm in radian mode. There we go. So then to do sine x equals negative 2/3, I can do inverse sine of negative 2 divided by 3. And I get this. I get negative 0.729,727,6562. Okay, so that's this angle here. But we want to be over the interval from 0 to 2 pi. So if we go ahead and take that angle, which is negative, and add 2 pi, we'll be able to come back around and get the positive version. Get that version right there. So let's do that. So let's add 2 pi. And we get 5.553457651. So we get around 5.5535. Okay, but that's not the only one that's going to be true. It's not going to be the only one where sine x equals negative 2/3. Remember the whole A-smart trig class. Everything's positive in quad 1. Sine's positive in quad 2. Trig, so you had tangent's positive in quad 3. Cosine's positive in quad 4. So if sine equals negative 2/3, that means you can have the angle either in quad 3 or quad 4. We've just handled the quad 4 situation. But we've also got to figure out the quad 3 situation. So if this angle is 0.729, etc., you can add pi to that and get this angle here. So if you take 0.729,727,6562 and add pi, you get around 3.8713 for that one. Whoops. And remember, this is in radians. And that takes care of both possibilities for this over the interval 0 to 2 pi. Remember, it's only over 0 to 2 pi, so we're looking at positive angles somewhere from here around to here. No further, no less, no more. And so there's only 2 quadrants where that can happen, where sine can equal negative over 0 to 2 pi, and that's in quadrants 3 and 4. And that's these 2 angles here. So our final answers include 3.8713, rounded, 5.5535, and then pi over 2. If you can get the answer exact, like pi over 2, leave it exact. Don't change it to a decimal. We had no choice on the sine x equals negative 2/3 to use decimals because we had to put in a calculator. It wasn't one of those that was really we could put into our unit circles. So that's where we went there. Okay, next up, let's say we have a problem where we need to use the quadratic formula. You guys remember that oldie but goodie, right? X equals negative b plus or minus square root b squared minus 4ac all over 2a. Yeah, that. We get to use that. Now that I've thoroughly terrified you guys with my singing, let's do it. All right. I'll jot the little formula down over here. X equals negative b plus or minus square root. I'll torment you again. B squared minus 4ac all over 2a. Okay. So to work with this one, we're going to solve for x. Since there's a 1 over here, I don't want to leave this factored. I'm going to need to distribute the cosine x. And then I'm going to go ahead and subtract the 1 from both sides. Get everything on the same side. But I quickly see, when I try to factor this, that it's not going to factor. So I'm stuck using the quadratic formula. In this case, the a is 1, the b is 2, the c is negative 1. But instead of x, we have cosine x. So cosine x equals negative b, negative 2 plus or minus square root 2 squared minus 4 times 1 times negative 1 all over 2 times 1. So we have negative 2 plus or minus square root of 8 all over 2. Negative 2 plus or minus 2 square roots of 2 all over 2. Negative 1 plus or minus square root of 2. Now cosine equals that. So x equals the inverse cosine of negative 1 plus square root of 2. X equals inverse cosine of negative 1 minus square root of 2. And we gotta see what happens from there. Alright, let's pull up the trusty old calculator. Clear that out, make it pretty. Alright, now, what mode am I in? I'm in radian, let's stick with that. Okay, so we're going to do inverse cosine of negative 1 plus second function square root of 2. And we get this. I'm not going to jot it down just yet. Now let's go ahead and do inverse cosine also of negative 1 minus square root of 2. Uh-oh. We can't do that one. If you put negative 1 minus square root of 2 by itself in, because I don't need, let me try it again. I don't know what I'm thinking here. Negative 1 minus square root of 2. You get negative 2.414213562. You cannot take the inverse cosine of that. This is not in the domain of inverse cosine, because the domain of inverse cosine goes negative 1 to 1. So that one's not going to work. You can only work with the 1.143717774. All right. So this one's out. And on this one, you get that crazy decimal. Okay, so that angle is right here. Now let's say you're asked to find all solutions. All solutions. Alright. Not only does 1.1437 work, but every time you add 2 pi to it, you're going to get back there, and that's going to work. Or you can subtract 2 pi and you'll get back there, and that's going to work. So go ahead and say 1.1437 plus 2n pi, where n again is an integer, element of z, the integers. But it turns out too, also, you got a smart trig class. If you're doing cosine of a, if your cosine equals something positive, not only is that going to work in quadrant 1, it's also going to work in quadrant 4. So what you can do too is do 2 pi minus that and get the other number. .143717774, and you get this. That's for the other quadrant. So if you're in quadrant 4, so here you got this angle, and then in quadrant 4, you're looking at that, you get about 5.1395 if you go ahead and round it. But you can also add 2n pi to get, you're getting all possible angles that'll give you that result. By adding 2n pi, you'll just get all the angles where you've gone around again, either clockwise or counterclockwise, and ended up in that same place. Okay, so that's an example of using the quadratic formula for this. All right, next example, we're going to use a squaring technique. You guys used this kind of technique when you were solving radical equations, like in college algebra. But you've quickly learned that if you square both sides of an equation to solve it, you could end up with something called extraneous solutions. And that's true here too. So you have to, when you square both sides, you have to check all of your solutions to make sure they work and toss out any extraneous ones. Check and toss out extraneous solutions. Okay, so let's start with this. Now let's say we have cotangent x minus square root of 3 equals cosecant x. And I might be looking at this and going, alright, there's a lot of things I could try here. Like maybe I could try changing cotangent to cosine over sine, and maybe I could change cosecant to 1 over sine. And that might get tricky having a fraction with sine on the bottom. But you know what? I do have an identity I know of where cosecant squared x would equal 1 plus cotangent squared x. And since I already have a cotangent here, maybe if I square both sides, I can then turn this into something where I can apply a known identity. Okay, let's try it. Let's see. On this side, when I square both sides, on this side I got a FOIL. Cotangent squared x. I'm going to end up with minus 2 square roots of 3 cotangent x plus 3. On the other side I have cosecant squared x. Hey, I know that cosecant squared x is the same thing as 1 plus cotangent squared x. And right there, that's going to be useful, because if I have a cotangent squared x term on both sides, I can subtract, and basically those are gone. Alright, subtract 3 from both sides, and I got negative 2 square roots of 3 cotangent x equals negative 2. And divide, I get cotangent x equals 2 over 2 square roots of 3, or 1 over the square root of 3. Okay. Now let's see here. They're going to ask us to solve this over 0 to 2 pi. So, 0 to 2 pi tells me I'm in radians. So where exactly does cotangent x equal 1 over square root of 3? Well, this is a problem I can tackle with my unit circle. And I learned that this happens at x equals pi over 3, also at x equals 4 pi over 3, when I'm looking at going through 0 to 2 pi. But I must check, because by squaring both sides back here in this first step, I could possibly introduce extraneous solutions. So I must go back and take each answer and plug into the original equation. Box that in to remind you, use original equation. Alright, so first check cotangent pi over 3 minus square root of 3 equals cosecant pi over 3. Well, cotangent pi over 3, I'm going to get 1 over the square root of 3 minus square root of 3 equals, and then cosecant, that's 1 over sine, I'm going to get 2 over square root of 3. On this side, I'm going to get negative 2 over square root of 3 equals positive 2 over square root of 3. And doesn't work. So pi over 3 gets tossed. Same process with 4 pi over 3. Check it in the original equation. Okay, 4 pi over 3. I've got cotangent would be 1 over square root of 3 again. So on this side I'm going to get negative 2 over square root of 3. But cosecant, I've got 1 over, the negative square root of 3 over 2, so that's going to give me negative 2 over square root of 3. That one works. So 4 pi over 3 is my only solution here. So I had two possible solutions, had to check them. Turns out pi over 3 was extraneous. Alright, just a few more. Those half angle and double angle identities, they can pop up here in these equations too. Half angle. Here's an example of an equation involving a half angle. Alright, you start out solving it like you did the linear equation, linear version. You can add square root of 2 to both sides, divide by 2 on both sides. Alright, and we're going to solve this over the interval 0 to 2 pi. Now if 0 is less than or equal to x, which is less than 2 pi, we're dealing with x over 2. So if we divide everything through by 2, we got 0 is less than or equal to x over 2, which is less than pi. So we're really concentrating on values from 0 to pi, where the cosine equals square root of 2 over 2. So the cosine equals square root of 2 over 2 at pi over 4 and at 7 pi over 4. So if cosine of x over 2 equals pi over 4, if cosine of pi over 4 equals square root of 2 over 2, we've got x over 2 in that space. So if x over 2 is pi over 4, then x must be pi over 2. If x over 2 is 7 pi over 4, then x must be 7 pi over 2. So there's your solutions there. But, x over 2, we're only going from 0 to pi, and this already goes beyond 0 to pi, so that's not going to be included. Okay, so the only one then that we're going to use is pi over 2, because x over 2 has to fall from 0 to pi, or x has to fall from 0 to 2 pi. Well, 7 pi over 2 here is really 3.5 pi, so it's outside of our values. But if they ask us for all possible solutions, then we'll use these. We'll use not only the pi over 2, but we'll use the 7 pi over 2. Because all possible solutions, go ahead and look around your unit circle all the way around, 0 to 2 pi, see what values you got, and then use those. Use those and see where you can go with them. Alright, this particular equation has the cosine of x over 2. Looking at the period, it's not going to be 2 pi because you have x over 2 over here. It's actually going to be 4 pi because it'll be 2 pi over a half. Alright, so if the period's 4 pi, then if you have a solution at pi over 2, you can add 4 pi. Or if you have a solution at 7 pi over 2, you can add 4 pi. And take it from there. Okay, so that's one of your half angle type situations. Okay, and n again is any integer, as usual. Alright, the next, let's say you have double angle. You can have a double angle one too. Alright, sometimes with the double angle ones, it just helps to replace things with your known identities. Like on this one, you can replace cosine 2x with 1 minus 2 sine squared x. And I chose that one because of having sine x already on the other side. And then I could turn this into a nice quadratic equation. This one's factorable. Let's see, for this factor, you're going to get sine x equals 1/2. For that factor, you're going to get sine x equals -1. You're doing it over 0 to 2 pi. If sine x is 1/2, that's true for pi over 6 and 5 pi over 6 in this interval, 0 to 2 pi. And if sine x is -1, that's true for 3 pi over 2. So there's your possible solutions to that equation. Alright, then let's do one more. And that'll be enough for now. Situation with multiple angle identities. Let's say you have something like 2 cosine squared theta minus 2 sine squared theta plus 1 equals 0. Well, this one, if you factor a 2 out right here, you got cosine squared theta minus sine squared theta, which is one of your known identities. That is cosine 2 theta. You're like, wait a minute, we just did a double angle one. What the heck? Alright, just bear with me here. Let's go ahead and solve for cosine 2 theta. It's going to equal negative. When you subtract 1 and divide by the 2, you're going to get equal -1/2. And let's look at solving this over the interval 0 to 360. So we're back to degrees. Okay, so theta falls from 0 to 360. But we've got 2 theta in there, so if we times by 2, 2 theta falls from 0 to 720. Times everything through by 2 there. So let's see. Cosine 2 theta equals -1/2. So 2 theta, where does it equal -1/2? If you go around your unit circle, you got at 120 degrees. You've got at 300 degrees. No, wait, we're looking at -1/2. Excuse me. We're looking at 240 degrees. Then our interval for 2 theta goes up to 720, so we can go back around. If you add 360 to 1, or if you add 360 to 120, you get 480. And if you add 360 to 240, you get 600. And then stop there, because if you keep going, if you go any further, you're going to exceed the 720. So we could go that high because 2 theta falls from 0 to 720. Then if you divide everything by 2, theta can be 60, 120, 240, or 300. And that's as high as you can go because theta falls from 0 to 360. And there you go. And if you want all of them, and not just in that interval, well, you could take 60 degrees. If you add 180, you get 240. And if you add 180 to that, you'll get back to that 60. And if you add, so just keep adding 180 and you'll flop back and forth between those two. Or if you take 120, you can do the same thing. Add 180, you get to 300. Add 180, you get to 480, which is in the same place as 120. And then you keep going back and forth between those two spots. So there's all the possible angles for that equation. Okay, well, I think that's probably enough examples. That's a little bit of everything that you might see in this little section with trig equations. So happy solving, and don't forget, read carefully what intervals you're in. If you're using your calculators, make sure you're in the right mode. And if you square both sides, don't forget to check for extraneous solutions. Thank you for joining us.